Howdy, we are the SOMAR system. I'm Connor Burke, and I'm joined by Vannesa Galvan, Jose Garza, and Guadalupe Rodriguez.
So the problem our system addresses is in the case where objects may need to be retrieved in a situation where the environment or the object itself may pose a threat to the lives of those sent in for retrieval. Our solution is SOMAR, or Swarm Object Manipulating Autonomous Rover, an efficient and autonomous solution intended for object manipulation and relocation through the use of unmanned rovers. A scenario where our system could be applied is in the case where retrieving unknown or potentially hazardous objects from an unstable environment.
This is a subsystem breakdown of our project. Connor has sensors and item recognition. He does passive scanning of the room, identifies objects, and helps with rover alignment. Guadalupe has rover navigation. Using sensor data, he has to align the rover so that we are able to pick up the object as well. Jose has swarm mentality. He communicates with other rovers to avoid collision and track their location. Lastly, myself, I am with object manipulation. I am in charge of the mechanical arm that retrieves the objects.
So a foreword to our entire presentation here. Due to the COVID-19 outbreak, we were unable to complete our projects as far as we wanted to, so keep that in mind as we present them. So for my subsystem, I was able to get the object detection and object depth to work very, very well and have them run concurrently, and also have it run with the object manipulation subsystem to where we could have all three of those going at the same time, be able to switch back and forth between them so that they could actually see an object and also see the space behind it so that we don't run into a wall or any other sort of objects in the room, and then have the arm pick up the object when it sees it. And then I was also able to determine our power supply using this Romos portable power bank. And just for the mounting system, we were just going to use simple L brackets to mount the plate for the cameras. And then there was another little just bracket system that we could use to actually hold the stereo pie that we were using in place. So for my data, I was able to show the detection rate for objects at certain distances. So we were detecting road objects in this case. And between 1 and 5 feet, it was highly accurate. But once you got out of that range, it sharply dropped because it was still looking for that color. And at that point, there's a lot of background noise, so it makes the color less prominent. And then for the depth, you can see here, as a object is closer to it, it is a cooler color. It's a blue and greens. And as it is further, it's the reds and oranges. So as my arm in this video moves closer and closer, it becomes a cooler and cooler color.
The progress for object manipulation, I was able to program 2 programs, the ideal and non-ideal situation. For the ideal program, the object is standing, and for the non-ideal, the object has tipped on its side. The programs were compatible with the sensor subsystem. We tested it before the break. And then I also proceeded to get rid of 2 degrees of freedom so that I can provide more power to other critical servos. This is a data sheet that I collected. So I have the minimum voltage required for each servo to work and the current needed. In the program, you're going to have to specify the PWM signal, and that's what the numbers represent. For example, on servo 3, if it's less than 7, then the servo turns left, and if it's greater than that, it's going to turn right. Using that data, I was able to create this arm code, and it starts in the upright position like you see on the right hand side picture, and then it's going to open the finger, the arm is going to drop, the finger is going to close to retrieve the object, and then the arm is going to come back up, and it's going to keep repeating this movement for every single object. We like to keep it consistent, and that's why we have 2 codes, one where the object is standing up and one where the object has fallen. We said that these 2 ideal situations would work for any scenario.
For swarm mentality, progress made to date includes time testings of data transmissions between XP-S2C modules, downloaded and installed MarvelMind software and drivers, established non-inverse architecture network and configured modem and beacons, assigned a mobile beacon, also known as a hedgehog, and interfaced the hedgehog with an Arduino Uno. Here in the bottom right corner, we can see a picture of the Arduino Uno being interfaced with the hedgehog. In the top right corner, we have a demonstration of real-time tracking where the hedgehog, you can see BEC moving around as the blue icon and the stationary beacons as the green icons. Data collected for swarm mentality includes in this table on the left, and the transmission timings, where we concluded that when sending different packets of data from the coordinator to the going from the coordinator to the router would actually take significantly longer than going from router to coordinator. And in the top right corner, I have a time test table of the lag for our indoor tracking. And I found that on average, it would take 1.8275 seconds for the updated location to be on track to where the current location is for the hedgehog. And in the bottom right corner, we can see a live the interface between Arduino Uno and the hedgehog and live updates.
This is the rover navigation subsystem, and this is an overview of what went into it. One of the first things I did was establish communication between the Arduino Uno and the Sabertooth 2x12 motor driver to essentially get the motors to move utilizing signal. This is, of course, with the battery. Then I did a base load test, or a naked load test, which is just a rover with no mounts, and measured its speed in feet per second, as well as the time it can operate at full load. Then the bigger issue we encountered in the semester was pathfinding, and I attempted the use of the inertial movement unit, or IMU, along with calculus and the tachometer before discovering the Marvel Mind beacons. And one of the first issues we ran into with the Marvel Mind was the software. For some reason, the drivers wouldn't upload to the device, like the beacons nor the modem. This seemed to be solely a device problem on my part for my computer, as I don't know what the issue is, but once Jose utilized them, everything worked perfectly. And as for the mounting, we were to secure the subsystem components like the camera and the arm on the rover without shifting the center of gravity at full extension of the arm. And then for the data slide, I just on the left I have a table of the speed test, which is just the markers set 1 foot apart, so you can see the time it took for the rover to get, from initial state to marker 1. And then I have an image of some code that we used for the IMU initially, as well as the distance equation.
What is left to be done is, of course, mount the arm and all the sensors onto the rover, develop the room mapping algorithm with real-time coordinates and the intercommunication between SOMAR mentality and sensor item recognition, now that we got those components working. Then we have to finalize the arm positions for object retrieval, because as it is mounted, I would have to change a little bit of the way that the arm drops and some of the angles, but it shouldn't be too bad. And lastly, we should build the other 2 rovers using the schematics and what worked from this initial one.
So to conclude, we were unable to complete rover assembly, test room mapping, or complete subsystem integration due to the coronavirus outbreak. But given the progress made and the time we had left, it was highly probable for our system to be completely integrated and tested by the end of the semester. As a team, various tools were learned, such as the Arduino Uno layout, C and C++ programming for Arduino, Python for Raspberry Pi, soldering skills, experience with circuitry, wireless communication through XB-S2C, and indoor tracking using Marvel Mind indoor GPS. Different various processes were learned as well, such as how to properly search for valid research papers and resources to gain insight, how to efficiently coordinate and communicate as a team, and various skills and tools for proper time management.
So on to our execution and validation plan. In this graph, you can see then the green stands for objectives that we were able to hit and complete. Yellow is for stuff that we had partially completed and or we're still working on. And orange is spaces that we couldn't do because of the COVID-19 outbreak. And if you look at the March 9th date, which was right before spring break, which is when the outbreak really hit and we couldn't come into class anymore and get all of our supplies, we were roughly hitting our execution plan there. We were a little behind on building the units, but we were on track to be able to complete it by the end of the semester. And now we'll move on to the live Q&A portion of our presentation. Thanks and gig 'em.